Menelaus of Alexandria is a Greek astronomer and mathematician that lived in Rome between 70 and 140 CE. He wrote Spherica in 3 books, but only one of the books survives. The first book defines the spherical triangle, which is one of his major contributions to mathematics. He is also mentioned in Ptolemy's writing, but not much else is known about him. Menelaus' theorem states that given any line that transverses or crosses the 3 sides of a triangle, not a vertex of the triangle, the sides will be divided into 6 segments, and the product of the ratios of those segments will equal 1.
Before we get into the actual proof, there's some background that we have to cover. For this proof specifically, we're going to go over similarity. Similarity basically states that two triangles are similar if they have the same shape but are of different sizes. Some of the criteria for similarity include angle angle, side side side, and side angle side. If all 3 corresponding angles are the same, then the two triangles are also similar. Angle-angle criteria states that if two triangles have 2 equal corresponding angles, then they are similar. That is because the sum of the angles of a triangle will always add up to 180. So, if 2 triangles have 2 equal corresponding angles, then the third angle has no other choice than to also be equal, thus making the 2 triangles similar. Side angle side criteria states that 2 triangles are similar if 2 of the corresponding sides are proportional and the angle between them is equal. Side 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 criteria states that triangles are similar if the corresponding sides of the triangle are all proportional. In this proof, we also use the idea of vertical angles. Basically, all it is if 2 lines intersect one another, the opposite angles are going to be equal.
Alright, now we're going to move on to the proof of Menelaus' theorem. So the first thing I'm going to do is draw a diagram of it. So if we have a triangle, this is going to be triangle ABC. So this will be point vertex A, vertex B, vertex C. If we draw a line through this, and the first thing I'm actually going to have to do is extend line AC out of it. So if we draw a line through this so that it hits each side and not hitting a vertex, that would look something like this. Now, what I'm going to do is I'm going to label these points, and this is vertex A. Alright, so I'm going to label the points where this line intersects the 3 sides. So this point where the line hits AB, I'm going to call H. The point where the line hits BC, I'm going to call G. The point where the line hits AC, I'm going to call point F. Alright, so we have 3 points where the line hits the 3 sides of the triangles, and notice that I had to extend this line, this side here, side AC, in order to hit that side. And in fact, I could have drawn this another way with the line lying entirely outside of the triangle, but that requires extending out the lines more, which is a bit harder to draw. So, but that case is, the proof is exactly the same. So this is the case we'll consider. So now, the theorem says the segment here, AH divided by HB. That do AH divided by HB, that ratio, multiply it by the ratio BG over GC, times the ratio of CF here over FA, which is this longer segment here. If you multiply those ratios together, you get 1. So the first step proving this is to draw some perpendicular lines to the line we drew. Alright, and this is called dropping a perpendicular, if you've ever heard that before. So, first thing, we're going to draw a perpendicular from point A, or vertex A, rather, to the line. So that's going to look something like this. And this will be perpendicular. Then I'm going to draw, right, this, where is it? This perpendicular from vertex B. This will also be perpendicular, or rather 90 degrees. And then the last one from vertex C, we have this. All right, and this will also be perpendicular. All right, now I'm going to call this point here point S. I'm going to call this point here R, and this R is this point here, H is this point here. So, oh, that's not what I wanted to do. All right, so at this point R here, we have this point S here, and we have this point where A hits it as Q. So we have Q, R, and S. All right, now I'm going to show that several triangles are similar. That's how I'm going to set up the proof. Now we've already discussed similarity. So here's the first set of triangles I'm going to prove are similar. So what I want you to do is consider triangles BRH, which is this triangle right here, this triangle here, and then triangle AQH, so this triangle here. All right. Now, so if we look at triangles BRH and triangles AQH. Now, let's look what's in common. So, we have this angle here, angle RHB, so this angle right here, angle RHB, that is equal to, or rather, if you notice, this angle RHB is going to be equal to angle AHQ, because those are vertical angles, and we already talked about that. So angle RHB is equal to angle AHQ. So, that's also not what I wanted to do. AHQ. All right, now what I want you to do is consider angle BRH. Notice that angle BRH is 90 degrees, and angle AQH. Angle AQH. Those are both 90-degree angles, so that means those are also equal. And what that means is that we have two angles equal in two triangles. Two triangles have two angles in common, then they're similar. So that means we can say that triangle BRH is similar to, this is the symbol for similar if you recall, triangle AQH. All right, so we've shown that these two triangles here are similar. Now I'm going to, can I scroll down? All right, I'm going to erase this. All right, so we just shown. All right, now rewrite this up here small. So we have triangle BRH is similar to triangle AQH. All right. I'm just gonna write them up here, up here, this to show that, so we can keep track of which triangles shown are similar. All right, the next set of triangles I'm gonna look at are triangles CSG, so this triangle right here, and then triangle BRG, which is here. So if you sort of follow the pin, this triangle inside of that line. So now, all right, so this is separate. Okay, so now I want you to look at triangle CSG, and triangle BRG. So let's see what we can find. So you can see they touch here at point G, and then what angles are these going to be? It's going to be angle CGS, And you can see that will be equal to angle BGR because those are vertical angles. As you can see, these two angles here, those are vertical angles because they're formed by two intersecting lines. All right. Now the next thing we're going to do is we're going to notice angle CSG. Well, that's pretty obvious because angle CSG and angle BRG are both right angles. So that means right angles are all equal. So we have two equal angles here. So therefore, we've shown that once again, two angles in each triangle are equal. And once again, by the AA similarity criterion. Oops, not what I wanted to do. So by the AA similarity criterion in triangle CSG, similar to triangle BRG. All right. Now, as you can see, this is very similar in each case. And we got one more set of similar triangles. All right, and once again, I'm going to rewrite this up here in our little notepad, so to speak. CSG is similar to triangle BRG. And once again, separate this off. All right, now the final set of similar triangles, and this can go a little faster because we've done this twice already. Okay, we're gonna, or what I want you to do is consider triangle AQF along with triangle CSF. 1 second. All right, and triangle CSF. All right, so if you see that, it'll be triangle CSF here, then this big triangle here. Sort of hard to see because all these other lines in there, but you can see triangle AQF. All right, so we erase all these extra lines. What are we gonna see is the same here because it's gonna follow the same pattern that we did to show that these two triangles are similar. So we already have two right angles like we've done in each case. So we write those down. Angle AQF will equal angle CSF. All right, because they're both right angles. Now here's where it's a little bit different from before. There aren't any vertical angles here. But if you notice, if you consider angle AFQ and similarly consider angle CFS, those will be the same because angle CSF goes CFS goes along here. So it's this angle right here. And then angle AFQ will also be this angle right here. So these triangles actually share the same angle, and an angle is equal to itself. That's obvious. So we have two angles in common. One angle, in fact, shared, but makes no matter to geometry. So we have two angles equal. Once again, like we've shown, triangle AQF will be similar to triangle CSF. And I have to erase this. We're going to have, and that, write this up here. Well, we're going to have three sets of similar triangles within this diagram. So this would triangle AQF be similar to triangle CSF. Now, the last thing I want to do before we switch over to show the algebra part of this proof is I'm just going to assign a couple letters. So I'll get rid of some of these. Just remember that these angles are 90 degrees. In fact, let's just go ahead and make that just leave those in there, but just make them a little smaller. All right, so first thing I want to do is I want to assign these different values. So length of AQ. So AQ, this line segment here, I'm going to give that length. So the length of that, I'm going to say that is equal to, what is it? T. All right, so T. And then what's the next one? So this comes from vertex A, so we come over here to vertex B, the perpendicular from vertex B, so it'd be BR. It's going to be side length U. Unfortunately, in mathematics, we liked letters U and V, and similarly, unfortunately, U and V look quite similar. So I'm going to do my best to make these look different. So BR will be U, and then finally CS here. CS will be V. So I hope these look distinct enough. This is U, and this is V. All right. So with all this in mind, I'll write this on the diagram V. Now we're going to switch, and next thing will be shown is the algebra of this involving involving these three values and these three sets of similar triangles to prove Menelaus' theorem once and for all. Or rather, we're going to show what we originally stated, and then afterwards I'm going to give a little bit more information about something cool you can do to extend this out a little bit. Alright.
Now that we have proven that the triangles in our problem are similar, let's take a look at how to create side ratios for general triangles. So, if you look at triangle 1 and triangle 2, we're going to assume that they are already proven to be similar. This means that the ratios of their corresponding sides are going to be equal. Now, in triangle 1, side AB over side BC is going to be equal to the ratio of the corresponding sides of triangle 2. Side AB connects the red angle and the green angle in triangle 1. In triangle 2, the red angle and the green angle are connected by side ED. BC in triangle 1 connects the blue angle and the green angle. The blue angle and the green angle in triangle 2 are connected by DF. Now, in triangle 1, AC connects the blue angle and the red angle. In triangle 2, the blue angle and the red angle are connected by side EF. And that is how we obtain these side ratios for similar triangles. Now that we've explored how to find the side ratios for generally similar triangles, let's try to apply those concepts to the triangles that we have in our problem. So let's look at the first set of similar triangles. We have triangle BRH is similar to triangle AQH. So let's label the corresponding angles. We know AHQ and RHB are going to be corresponding because of the vertical angle property. We know that BRH is going to be equal to AQH. And you can just read that from the way that it's written in the similar triangles. And then the third angle is going to have no other option but to be equal. So angle QAH is going to be corresponding to RBH. So let's write the ratios for those. The yellow angle and the orange angle are connected by R and H. And let's label these triangle 1 and triangle 2. So in triangle 1, the yellow angle and the orange angle are connected by R and H. In triangle 2, the yellow angle and the orange angle are connected by H and Q. In triangle 1, the purple angle and the orange angle are connected by B and H. In triangle 2, the purple angle and the orange angle are connected by A and H. So RH was from triangle 1, so BH needs to be on the top of this ratio over AH. Okay, our last set of angles is going to be yellow and purple. So in triangle 1, the yellow angle and the purple angle are connected by R and B. In triangle 2, the yellow angle and purple angle are connected by A and Q. Okay, so we have these side ratios, and if you notice, side RB is nothing but U, as we previously labeled it, and side AQ is nothing but T, as we previously labeled it. So these are going to correspond that. Okay, our next set of similar triangles are going to be triangle AQF and CSF. So triangle AQF is going to have corresponding angle AQF and CSF. So let's call this triangle 3, and this can be triangle 4. We also know that AFQ, this angle here, is going to be equal to CFS. If you notice, they are the same angle because triangle CSF is a smaller triangle lying inside of the bigger triangle AQF. They share a vertex, so they're going to share that angle. The other angle has no other choice but to be equal, so angle QAF is going to be equal to angle SCF. Okay, so let's connect the correct side ratios. The purple angle and the blue angle in triangle 3 are connected by Q and A. Triangle 4, the purple angle and the blue angle are connected by C and S. The blue angle and the green angle in triangle 3 are connected by A and F. The blue angle and the green angle in triangle 4 are connected by C and F. The purple angle and the green angle in triangle 3 are connected by Q and F. The purple angle and the green angle in triangle 4 are connected by S and F. And again, if you notice from this ratio here, QA is nothing but T, and CS is nothing but V. So we also have this set of side ratios here. Let's find the side ratios for triangles BRG and CSG. So triangle BRG is going to share the angle BRG and the angle CSG. It's right here. Then we have GBR, this angle here, GBR, is going to be GCS. This angle right here. And as we've shown previously, the other angle has no choice but to be equal. So in triangle BRG, the only angle we have left is this angle G here. And in triangle CGS, we have the vertical angle being equal there. So the side ratios for those If you look at triangle BRG, please pay attention to the blue line this time. I know the yellow line's already there, but that's from a different side ratio we created. So BRG is the blue angle. The blue angle and the green angle are connected by sides B and R. We'll call this triangle 5. This will be triangle 6. So in triangle 5, B and R are connected by the blue angle and the green angle. In triangle 6, the blue angle and the green angle are connected by CS. The blue angle and the purple angle in triangle 5 are connected by R and G. And the blue angle and the purple angle in triangle 6 are connected by G and S. The green angle and the purple angle in triangle 5 are connected by B and G. And the green angle and the purple angle in triangle 6 are connected by C and G. And again, if you notice, CS is nothing but V, and BR is nothing but U. So we have also created these ratios. Now that we have the ratios and we know exactly what we're trying to prove, we're going to try to manipulate these ratios to make them fit into our proof and get our desired answer. So the first thing that we want to focus on is this AH over BH. That is going to be coming from the similar triangles BRH and AQH. Now we know with ratios that we can flip them. So right now we have BH over AH being equal to U over T. We can flip both of those ratios and say that AH over BH is equal to T over U. Now if we look at BG and CG, we know that that is going to come from BRG and CSG being similar, and that ratio is going to be U over V. Okay, CF over AF is going to come from AQF and CSF being similar. And here we have it listed as AF over CF, so let's go ahead and flip that. So AF over CF is equal to T over V. So CF over AF is going to be equal to V over T. Okay? And if you notice, we have found what we wanted to find. So we have this TU is going here. This U over V is going here. And this V over T is going here. Now that we've proven that this equation holds true, we need to think about what it actually means. So we have that the product of three non-adjacent segments, which comes from the definition of the theorem, so AH, BG, and CF in our triangle are non-adjacent. BH, CG, and AF in our triangles are also not adjacent. We see that the product of AH, BG, and CF is going to be equal to the product of BH, CG, and AF. This is what makes the whole entire ratio equal to 1. We can look at this ratio from an algebraic perspective and also determine what it means. So if I'm going to be multiplying these ratios together, we're going to have AH times BG times CF, because remember when you're multiplying fractions, you just multiply across the top and then across the bottom. On the bottom, we're going to have BH times GC or CG, whichever you prefer, and AF. And we know that this ratio is going to be equal to 1. That means that the top part of the fraction and the bottom part of the fraction must be equal. For example, 2 over 2 is equal to 1. We know that 2 is equal to 2. So in order for a fraction to be equal to 1, the top and the bottom must be equal. So we can assume by this theorem that the product of AH, BG, and CF over the product of BH, CG, and AF is going to be 1, meaning that the product of the numerator is going to be equal to the product of the denominator.
We are now going to go over the converse of the proof. If 3 points L, M, and N lie on sides BC, CA, and AB respectively, such that AN over NB times BL over LC times AM over MC is equal to 1, then points L, M, and N are all collinear. We can do this by plotting a point N prime, which is the intersection between LM and AB, such that we get a new ratio that states that AN prime over N prime B is equal to, times BL over LC times AM over MC is equal to 1. From here we notice, from our original ratio up here, that AN prime over N prime B is the same as AN over NB, giving us that N prime is simply equal to N, making it so that L, M, and N are all co-linear.